Yeah, thank you very much. So yeah, it's a pleasure to be here in Newton Institute, this very nice program. Talk about that, and I should also thank Herbert for giving such a very beautiful talk about GHG just before me, so that will help me a lot for my talk. So this is about very recent work, actually not yet published, with my student Friedrich Hübner, about trying to derive the equation of generalized hydrodynamics, so kind of a proof of the GHG equations, in a quantum model, the Lieb-Liniger quantum gas. Okay, so I start with the model just to put it in context. So this is a model of n quantum particles in interaction with a delta function interaction, so hardcore particles which are otherwise free. And this model is known to be integrable for quite a long time. Of course, it admits momentum and Hamiltonian, and also infinitely many higher conserved charges, which actually corresponds to kind of higher derivatives here. So like nth derivative plus additional terms. Okay. So we've seen in the talk of Herbert that the generalized Gibbs ensemble are important. So in particular, in this model, if you look for the natural stationary states, they're going to involve a lot of kind of a temperature or generalized Evers temperature. And this model is interesting because it is, well, because it is integrable, but also it is experimentally realizable in cold atomic gases. So it's actually something you can check in experiments. Okay. Now, yes, okay. So we're looking for the hydrodynamic scale. So what we'd like to do is understand what happens if you start with a state which is inhomogeneous. So here is a very simple way of putting an homogeneity in the state. I think about some thermal state with an external potential that couples to all the particles in the same way. So this mu is not really important, with some function v of x, which is slowly varying in space, so some long wavelength function. The typical initial state you can start with. And you look at the quantum evolution of observables and try to see what happens at large space-time, essentially. Okay, so this is a slowly varying initial condition and typical situation where you'd like to do hydrodynamics. Okay, now we've seen in Herbert's talk that actually the notion of hydrodynamics that comes out in these integrable systems is based on generalized Gibbs ensembles. Essentially, in every fluid cell in space-time, what you have is that you have a generalized Gibbs ensemble with temperatures that can depend on space-time. Okay. So you have xt dependence betas, but you have infinitely many of these, and so eventually you get infinitely many equations. Okay? So if we write that in an equation, so the average of a local observable at xt in that setup where you start with some long wavelength initial state is going to be very well approximated at large space-time by the average of that observable in one of these stationary states representing the fluid cell. Okay? And these stationary states will be characterized by these inverse temperature that now depends on where you look at the observable xt. Okay, so that's the hydrodynamic approximation, and that's it. And then you get the hydrodynamic equation simply by writing the continuity equation for all the conservation laws. So every conserved quantity has with it a density and a current, and you write the continuity equation for all these densities and currents. That's an equation then for the betas. If you know how to calculate the conserved densities and the conserved currents, then you have an equation, and Herbert showed us, the formulas for calculating conserved densities and currents. Okay. Now, this is a kind of a very, very formal thing, and as Herbert showed, there's a very important concept behind that. In order to get some actual useful equations from this is a scattering principle. Okay, so let me explain to you. So what I want to do is, say what are these GGEs? How do I describe them? Using the scattering ideas, and that's what's going to be absolutely fundamental then in my derivation of the GHG equation, the scattering ideas. Okay, so one of the properties of integrable many-body systems, including the Lieb-Liniger model, is that the scattering processes are elastic and factorized. So now kind of forget about this initial condition that is homogeneous. Now think about particles kind of going towards each other, interacting, and coming out. Okay. So elastic and factorized, what does that mean? Well, it is simplest to express that using classical particle trajectories. I'd like to do that in the quantum case here, the Lieb-Liniger model, but it's simplest to express using classical trajectories. So basically, your trajectories of particles at very large time, positive or negative, will look, if the interaction is repulsive, like straight trajectories with different momenta. Okay, so there's the in momenta for negative time, the out momenta for positive time. That's completely general. Okay. Plus some shifts, which are called the impact parameter, also depending on in and out. And the main point about elastic scattering is that the in and out momenta are the same sets of momenta. So this is quite non-trivial. In general, you don't have that, but because of integrability, that's the case. Okay? So for that model, for instance, in the particle picture or in the soliton picture, this is what's happening. And also the point about factorized scattering is that the impact parameters are related to each other in a very simple fashion. Essentially, the shifts between the out and the in impact parameters is simply obtained by accumulating the two-body shifts of every two-body interaction that you'd have in this whole scattering process. And we should think about that where you have some shift from some direction if the particle comes from the left or from the right. So essentially, this is the picture, right? You want to know the shift of that particle. You look at the shift it has occurred with this other particle here plus the one with this other particle there. What is the shift? Well, it's just a two-body shift in a system of particles that preserve energy and momentum in one dimension. When you have a two-body interaction, the momenta before and after hours are the same, and the only thing that can happen is a shift of trajectories. Okay, so essentially, you just accumulate these two-body shifts, and this is what gives you the difference between impact parameters. This is factorized scattering, and this is elasticity of scattering. This is complete general properties of many-body integrable systems. Now, the scattering coordinates in these integrable systems can be seen as action angle coordinates. So the action are the momenta because they are the same before and after. They don't change in time. Actually, they kind of conserve quantities. Okay, the momenta, and the angle coordinates are these impact parameters. Angle is not a very good word because it kind of you have the idea that it's something compact, but here the impact parameters are non-compact. It's on the line, right? Still, okay, they evolve trivially. So these impact parameters on the, you can see this mapping from x's to p's and y's as a change of coordinates, a canonical change of coordinate. And if you evolve the system, you can then think of evolving these asymptotic coordinates, and the p's don't evolve, the y's evolve linearly. Now you can do the same. This is a classical picture. I would like to do the Lieb-Liniger model, which is quantum, right? Well, you can do the same for quantum models, and what kind of represents all that is that well, you can construct out states and in states in similar way as in classical by kind of wave packets and all that. And the situation is that the in states and out states, where the scattering matrix is diagonal in momenta, so the in state and out state are related to each other with the same momenta, and with a phase which is the product of the two-body scattering phases. That's the idea, the same idea in the classical case, but in the quantum case. Now, why is this important? Well, the point about GGE is to use that in order to describe the GGEs in a kind of useful fashion. So here's the gas. Now, again, it's a classical picture, but something similar in a quantum case. Now, this is your gas. Take a little fluid cell here and see what you want to describe this fluid cell. It's in a GGE, the GGE of that fluid cell. So what you do? Well, you simply kind of take it out of the gas and put it in the vacuum. I think Herbert described that a little bit. So put that in the vacuum. The fluid cell is kind of large enough to include a lot of particles, but small enough so that the variations, you don't see the initial variations in your model. Okay. So you take that and then you kind of let it expand. This is this time of flight experiment that you can actually do in actual experiments, So let it expand and see what momenta you come out of that. Okay. Now the point, the idea behind GGE is that this distribution of momenta is a good conserved quantity to take as your set of conserved quantities to write your GGE equation, right? So this is kind of the soliton distribution that Herbert was talking about, right? So you take these, you look at these momenta, and you can define this rho of p comma x, x because it depends which cell you look at, and p because you have different momenta you look at, right? And you normalize it appropriately. This is the density in phase space. And this is that rho now that is a good conserved density for which you can write a continuity equation. That's the idea of a GGE, okay? Now, how do you write the continuity equation? Well, you need to know the current. So what is the current? Well, so Herbert told us there's this non-trivial effective velocity that comes out. So it turns out that if you just multiply this rho by an appropriate function, that is a functional of rho, actually. So this is non-trivial functional of rho. That is the correct current, and then you write your continuity equation, the hydrodynamic equation, simply by writing the continuity equation for this density in that current. Now it becomes it's as if you, instead of taking a discrete set of conserved quantities, you take a continuum of conserved quantities parameterized by the momenta. Okay, so this is kind of an explicit way of defining your rho of p by fluid cell and expansion, and writing your current and all that. So this is kind of GHD. And as we've seen, this effective velocity, although it is derived by a number of ways, are some very beautiful, some more complicated. And the last one that Herbert explained with Takatoshi is, I think, the most beautiful and the most general. You get this formula. This formula has a nice interpretation in terms of multiple scattering event, right? So you look at, so you take one tracer particle, let's say, in your system, and you assume that it interacts, by a set of two-body interactions. Even if it's a dense gas, you kind of assume as if it was not dense, and you count, the total shift. So here is the kind of probability that the interaction between particles happen. This is the shift times the density of particle, and you get the effective velocity like that. Now, there's no proof, as far as I understand, that actually uses this picture. This is a posteriori picture. You derive the currents in other ways, and then you reinterpret that in this way afterwards. And you say, oh, this is very nice. And when you give a talk, this is what you explain, but you never explain, well, you rarely explain the actual way of deriving the current, except in the previous talk. So, okay, now you say this is a very classical picture. What about in quantum system? Well, quantum system, of course, is a bit more complicated, right? I mean, you don't have particles, you have wave functions and all that. It's a bit more complicated. Well, it turns out, again, this is like a result of computations using our kind of technique, including Bethe and Zas technique, that do not do that, but that do other things, constructing the currents and all that. It turns out that the same formula holds also in the quantum system, in particular in the Lieb-Liniger model, where this shift, this two-body scattering shift, is nothing else but the semi-classical scattering shift. So the derivative of the two-body scattering phase in a two-body interaction with respect to the momenta. It turns out, okay, that's kind of an observation a posteriori, okay? So this is GHG and idea of GHG. Now, this is very nice, and what I want to get to is, how can we prove that? I'm not going to provide you a rigorous proof, of course, but kind of a path towards possible rigorous proof eventually when you deal with all the O of epsilons and all that in the Lieb-Liniger model. But before that, there are proofs actually of the GHG equation that are known. The basic one, well, okay, so before that, the problem with the picture that I've just given you, if I want to do a proof, well, one of the problems is indeed what are these momenta there. I mean, I define rho by saying, take out a cell and expand the particles. I can define it that way. Experimentally, you can do that. But mathematically, how do you calculate this, right? Spectral techniques and all that allow you to do that. But somehow this is a bit complicated. So you've got to have that. And more than that, you have to have this rho p comma x. So you have to be able to identify within new gas, like within the Toda picture that you have, where is the particle with what asymptotic momentum? Are they asymptotic momenta? You just see them when particles are very separated from each other. So this is a difficult problem. Where is the quasi-particle? The quasi-particle is somewhere in your gas, right? So you have so this kind of a non-trivial problem to do that. Okay. The other thing is calculating the currents. In fact, there are a lot of techniques. So actually, this is not too bad. It's quite well done. And the last thing, of course, which is absolutely non-trivial, is that this whole thing is based on the hydrodynamic approximation, and then writing the continuity equation. You've got to prove the hydrodynamic approximation and then the continuity equation. So it's rather non-trivial. Well, the actual proof that has been done, not based on this picture. This is the physical picture under GHG. They're based on the different techniques. In fact, there are various techniques. One of them is for the hydrogen gas, where actually here the kind of idea of the proof is relatively simple and easy to follow. And techniques, the details, of course, there's quite a few details. The first thing in the hydrogen gas is a gas of particles which are not point-like but have little rods, have a length. Okay, so it's a bit like the Lieb-Liniger gas, if you wish, right? They are free except at contact interaction where they exchange momenta, it's kind of delta function, but they have a little length and it's the classical model. Okay, now this is very nice because if you look at this gas and kind of do the expansion experiment, and look at where the momenta are there at large time, well, it's very easy to guess, at any time. It's just the momenta of the rods themselves. Because the interaction time is infinitesimal. So when the rods collide, they exchange momenta, and that's it. So you look at the rods here, and you immediately see what the asymptotic momenta are. So it's much simpler than Toda gas, where you don't see the asymptotic momenta. Okay? So in addition, more than that, you see where where they are, you can attribute a precision to them. So you can construct a empirical density, which is just sum over I delta x minus I xi of t, p minus pi, where xi of t are the trajectories of the rods. And that's a perfectly fine density that represents in the large scale limit, kind of a weak large scale convergence, a density of state for your hydrodynamics. Okay. So that's good. And the second thing is that now, what do you do to get hydrodynamics? Well, there's a trick, and the trick is that you map these non-trivial trajectories. They're not so non-trivial, but kind of still non-trivial, to trivial ones, which are trajectories for free particles. There's a mapping you can do. This is known for a long time. I don't know who first thought of this mapping, Possibly Herbert thought about that in the 70s, I don't know. But there's a proof in this paper that uses that. And just saying, essentially, collapse out the rods to points. And when you do that, you see that trajectories are just free particles. So in the mapping, I call it x to y, mapping my y coordinates are just the free particle coordinate, the x are the non-trivial trajectories. And the relation is just y is x minus the number of rods, before that x, essentially. Okay. So now when you have free trajectories, it's very easy to write a hydrodynamic equation for free trajectories. It's very easy. I mean, what's the equation for free particles? The hydrodynamic equation for free particles is the Lieb-Liniger equation of conservation of phase space, nothing else. That's it. So if you take the GEV equation and specialize to free particles, you get Lieb-Liniger equation, right? So, okay. So you write your Lieb-Liniger equation for your y trajectories, and then you apply on that Lieb-Liniger equation that mapping, and you get a GHD equation for this density. That's how it works, okay? And you can work out all the details, but essentially that's how it works. So you see, it's not about local thermalization and all that. It's about identifying new quasi-particles and then making an appropriate mapping. Okay. For instance, for the hard gas, there are proofs. As we know, with soliton gases, by using Whitham modulation theory, very different concept of proof. It's not about identifying your quasi-particles. It's a different thing. You start with some solutions that represent quasi-periodic solutions. You map to you go towards soliton gas limit, and you make this slowly varying in space, and then you ask for this to be a solution to your KdV equation. Okay, very different. Box cellular automaton, I think Herbert quickly talked about that. This is a cellular automaton where we have box that jumps onto boxes. And again, there you can identify solitons and do a bit like the hard rod and do something with a contraction. Hard rods with many different rod lengths has been done recently, but I think it's not yet published. But the main proof yet for integrable quantum models, non-trivial, right? For free is a linear function, but for non-trivial is no proof yet. Okay. Now, so I'd like to propose a path of proof. So here is so now it becomes a bit more technical, sorry, but okay. So here's the Hamiltonian again, is the Lieb-Liniger gas. Now there's not known about it, in particular, the exact eigenfunctions are known as the beta ansatz, right? So here's the beta ansatz eigenfunction. It's just a free radical, the IPX, plus some phase that actually represents the factorized scattering, okay? And the phase can be written explicitly as a sum over, sine of x I minus xj times this two-body scattering phase phi. Okay? And phi is known explicitly the arctangent. If you take its derivative, that's the object we're interested in, explicit function of momenta. Okay. Now there's a sum of permutation because this is a bosonic model, so there's got to be a bosonic wave function and some normalization constant. And the wave function, I'll do this a sign there. It looks like it has jumps, right? There's jumps in it, right? But in fact, there's no jump when you sum over all the permutation. It becomes just a function with cusps. And then when you take the derivative of the cusps, you get a delta function. That second derivative of cusp is delta function. And that's why you satisfy the Schrodinger equation. Okay, so that's how it works. So this beta and that's wave function. It diagonalizes the Hamiltonian, the momentum, and all higher conserved quantities with just a sum of the momenta, pi to the n. One can check that. Okay, and this also an autonomous set of functions on the line. So you can think of that as scattering states. Beta and that scattering states. Okay. Now, in order to kind of do something, I have to write an appropriate initial condition, right? This is crucial if I want to do then evolution. What's my initial condition? For that, I need to interpret appropriately these wave functions. So it is known that this is also Herbert mentioned that if I take this wave function and put it in a vacuum, so I take the wave function between 0 and L as is, and then the rest is 0, and then let it expand. It's not an eigenfunction if I put it in a vacuum somewhere and just 0 and L. If we expand what I'm going to see, I'm going to see nice wave packets, separated wave packets at different velocities, and the velocities are exactly these p's. So the p's that come here in the free part of the wave function are exactly the asymptotic momenta in that beta and that wave function. So this is very nice. Beta and that allows you to see the asymptotic momenta and the position at the same time, like for the hard rods. Okay, so and in addition, this wave function also is related to this wavelength symbol. It is known that if you now put the whole system of a finite box, then L, and take your wave function to be periodic, then you have the beta and that equation because of the periodicity. Well, if you take L and L large, number of particles and length large simultaneously, well, there's an equality for you choose your p's, of course, to give some kind of nice distribution in the large scale, and there's an equality with the generalized Gibbs symbol for some conserved quantity. which constant quantity is something that is related to your distribution of P, rho of P, by something called the thermodynamic Bethe-Ansatz. It's been worked out for quite some time. So there's a relation between that really a single wave function and a trace Gibbs state in the large L. Okay. So we use that and we propose the following initial state. Okay. Now this is not an eigenstate. This is not an invariant stationary state. It's a state where I do some modulation, a bit like the modulation theory, right, of a soliton gas. I take my wave function as it is, but I modulate for x. I modulate the amplitude with some function f. Okay. So this is the amplitude modulation of the state. I can do that, and if f varies on large scale, there is a slowly varying function f, then locally this will look like an eigenstate. So will, since eigenstates are like GGE, it will look like a GGE. For local observables, it will look like GGE. Okay. And in addition, well, the p's that I have there in this local cells, I can identify them with asymptotic particles. Maybe I can construct something that kind of makes sense, some GG. Okay, so this is my initial condition with some slowly varying f. Again, I have some overpermutation. The sum of permutation does not play a big role here. Okay, it's directly that. So, okay, this is for the sake of the start, I concentrate on that. One can go further and talk about long wavelength operators and go a bit further. I'll discuss that at the conclusion. For now, this is my initial condition. And then I'd like to do evolution, proper quantum time evolution, no approximation of fluid cells or anything like that. Proper, no, you don't have to look at conservation laws, whatever, right? Just time evolution with the full Hamiltonian. Okay. And what I want to show is that when you time evolve this, it's like changing, is just changing your slowly varying amplitude, okay, in a way which is simply by moving your x coordinates according to some trajectories. Okay. So that's the heart of it, why you're going to have a GG equation. So the slowly moving amplitude becomes a slowly moving amplitude with moving x's with some trajectories. And I want to show that these trajectories, show you what they are. If I construct their empirical densities, like in the hard rods, this in the large, kind of the weak limit of large scales satisfies the GG equation, like in the hard rods. But now with an non-trivial velocity corresponding to the Lieb-Liniger model. Okay, so that's the idea. So this is now if I want to connect that with actual average of local observables, there's a bit more work to do, but eventually it's possible. And for now, I just concentrate on the evolution of the wave function. Okay, and now of course, if I have free particles, if the phase, the scattering phase is zero, which is free particles, this is a very simple exercise from quantum mechanics 101, let's say. What you find is the trajectories are those of linear trajectories of free particles. Okay, but now they are modified because of the interaction. Okay, so that's the thing to prove. And once I have that, I essentially have the GG equation for the Lieb-Liniger gas. Okay, now what are these trajectories? So here is what I call the Bethe-Ansatz scattering map. So this is a map between y and x. It generalizes the hard rod thing again, right? The hard rod thing where we have x's, we kind of collapse them into particles, and we have the y that we're evolving trivially. Now I introduce this different map. So there's a sign in it, but I need to regularize it to make sure that things are nice. I regularize it with some epsilon here. So this map is not just shifting the x's by whatever there is on the left. It shifts by the scattering length, right? The 5 pi amplitude. And it's not just particles on the left and right, it's both sides. That's a technical detail, it doesn't matter too much, okay? But it kind of shifts the particles a little bit, okay? And it can be shown that this is by ejection Rn to Rn, this x to y. So this is kind of a nice map, okay? The Jacobian is strictly positive, okay? Now I want to make this a dynamical system, and so what I do, I simply start evolving the y in a trivial fashion, like in the hard rods, right? So this becomes now trajectories. So the x's have become trajectories. And check what the trajectories look like. They're different from the hard rod. The particles get stuck together for a while and then go away. And so the difference here is that the phi is positive instead of negative. So the interaction is attractive instead of repulsive. And so they get stuck together a bit more instead of kind of going far from each other as much as possible. But you can construct the trajectories. And it turns out you can show that this dynamical system is a factorized scattering dynamical system. So if you look at large time, you get straight trajectories with these PIs with some in and out impact parameter whose difference is exactly what it should be for factorized scattering. For this phi being the two-body scattering shift. Okay, so this is a nice dynamical system which is factorized scattering for every possible choice of positive phi. In fact, and you can put the Lieb-Liniger model in there. Okay. And in fact, if you wonder what these y, well, they are just the average of the in and out impact parameters, and that's why they vary trivially. Right? That's why. So, okay, so this is a set of trajectories, and you can show. This is a little arguments. One can make arguments a bit more precise, and eventually, I suppose, one can make the argument rigorous. But you can show that the densities of particles in phase space for this dynamical system satisfy the GHD equation. So it's a factorized scattering system that gives the GHD equation. It's just classical trajectories here, right? So how do we show that? It's actually very simple, like in a naive way, where you construct your empirical densities for momenta and positions, and you see that its derivative with respect to time gives you a continuity equation with this x dot there. X dot is the velocity of these trajectories. And x dot, well, you can build it. Well, sorry, I come back. You can just take the x dot of that, with y dot equals pi, and you get that equation. If I didn't make a mistake, you get that equation, and that equation looks very much like the effective velocity equation. And indeed, in fact, if you assume, and this can be justified a posteriori a different way, that the x dot I, if you go in large scale enough, actually is a function of the pi and xi only. So it's a function of what momenta you are and where you are only, which is what you would, typically have if you have a kind of a gas. Okay, then you exactly get the effective velocity equation. So this kind of trajectory immediately gives you the effective velocity equation and the GHD equation. It's kind of a very simple system, generalizing the Hydra system, which I think you can make that relatively rigorous. Okay. Now, what do you do with this? Well, you want to consider your slowly varying wave function. Now, the slowly varying wave function, the way that you deal with this is what we call the Beatty Fourier transform, where you do a Fourier transform after this Beatty and that scattering map. So Fourier transform in the y variable. You can do that. Y is bijection, so you can do that. Okay. And since f is slowly varying, then also as a function of y is slowly varying, so actually you can restrict the support of this Fourier transform to some small regions in momentum space. And that's actually the key of this whole thing. You go to small regions in momentum space. And from that, then you can show that the slowly varying wave function takes exactly the form of a linear combination of these Beatty and Zest eigenfunction around p with small variations around p. Small variations because this f is slowly varying, so these q's are just supported on a small shell around these p's. Okay, and that is just a consequence of Taylor expanding the phase in the beta as wave function for small q. The Taylor expansion phase for small q gives you the phase at p plus q times this y of x. Y of x is exactly the scattering map. Okay, so it's just a simple calculation, and it works. You have an epsilon there, you have to take care of the epsilon and all that. Of course, you have to take care of these higher q square, but you can argue that in appropriate regime, this would not matter. Once you have that, the time evolution is simple because you know how to time evolve these eigenfunctions. Okay, so you do time evolution, and you get just e to the IPQ times t. There's a t missing here with the overall phase, and if you neglect the q square term, in the end, what you get is that the time evolution of the Beatty Fourier transform is just a simple phase, linear phase. And when you map back to this ft, well, you get these trajectories. And that's it. Now, all this works if t is much smaller than L square. L square is a typical length because, well, so you can look at the computation. Now, that essentially it works if you are in the ballistic regime and not in the diffusive regime. T square will be diffusive. And then you have other effects, which maybe you could compute. I don't know. Okay. So, okay, that's it. Now, of course, if you want to go to actual average of local variables, you have to do a bit more work, which you can do. In fact, you can define long wavelength operators, for instance, operator that calculate this phase space density by saying that it maps eigenfunctions to slowly varying eigenfunctions. And from that, and using clustering, you can actually get the GHD equation for actual averages. So in principle, you can get to the full GHD equation in Lieb-Liniger model. And yeah, so these are further directions and questions. And that's it. That's what I wanted to say. Thank you for your attention.
All right, we have time for one small question.
Okay, so the proof seem to rely on the fact that it's your starting states resemble an eigenstate, not on GGE. So where did you use GGE?
Yeah, so actually, well, in the way that I've explained it, it kind of relies on that fact for the initial state. Okay, but in fact, one can go a bit further. So you can write some more arbitrary linear combination of eigenstates and evolve not the eigenstate, but evolve the operators themselves. I mean, you can take any state, whatever state you want, and evolve the operators themselves. You just have to define the operators appropriately, and you can define them by using these amplitude modification of the eigenstate. And that's okay because these amplitude modification are generic small shell integration of your Berti eigenstate. And generic small shell integration are generic long wavelength operators. So you can define a density, a spectral density operator, which is kind of a long enough wavelength, kind of mesoscopic. In particular, by saying that this, for again, F maps to psi PF, and you can show that actually with this, you will give you, if you integrate to R of X, the total charge with the correct charge density. Okay, so, and once you have that, then you just have to evolve the operator itself. You get a GED at the operatorial level, and then what you will need from that to get actually GED for averages is clustering of the states. Clustering of the states for GGE or for thermal state is quite okay. So I mean, but there's a little bit more work there to do for clustering. But yeah.
Thanks.
Okay, thank you. So let's thank Benjamin again.